Hey everybody, this is just the in-class lesson from, what is today, the 3rd? May 3rd. So we're just going to run through a warm-up problem and then a bunch more examples of the rotational solid stuff. And then when we're done, I'm going to post this because there's a lot of people that aren't here today. So you can just get caught up. And then tomorrow we'll wrap this up and practice a lot of stuff. And then we'll be doing practice AP questions on Thursday and Friday. So here is the warm-up of the day. The intermediate value theorem is the topic here. Some function, it's on a closed interval from 2 to 4, where f of 2 is 10 and f of 4 is 20. It can be helpful in these cases to just sketch a quick picture. Doesn't need to be any sort of to scale either, but you know the point 210 is on this line, and you know the point 420 is on this line. And that's it, and it's just a function that connects those. It's continuous, so there's no tricks there. So which of the following is guaranteed by the intermediate value theorem? I'm going to go ahead and just circle A. A is the correct answer. We'll talk about why. Let's talk about why B through E don't work. F of 3 could be 15, but there's no guarantee that it's at 15 when x is 3. So that's that. There's nothing about there being a maximum on this interval. The function could just look like this and doesn't have to have a maximum at all. F prime is 5. I mean, maybe. Could the slope be 5? Sure. The slope could be something close to 5, where maybe you have like a tangent line with a slope of 5. You could, but you don't have to, so that's out. And then question E says that the derivative is always positive, and not necessarily. I mean, you can draw a little curve looks like this, maybe decreases for a little bit, like that. So it doesn't have to be E either. But the intermediate value theorem says that at some point you do have to cross 13, because 13 is in between 10 and 20. So what the intermediate value theorem says is that somewhere in between 2 and 4, you are going to need to cross that line, at least once. So it is true, according to the IVT, or intermediate value theorem, that you do have to hit 13 some point in there. So that's why it's A. That's a pretty straightforward one. So, okay, let's get to the lesson today. If you're following along later on, we're looking at, oh, this is the wrong document. We're looking at 8.1.4 today, which is the last section that we're going to look at from this textbook before we cut and do a bunch of practice problems and then practice for your AP test on Monday. So we're going to look at a bunch of different cases of the 3D revolution thing and think about how a bunch of different how things would change depending on what's happening. So the first question, 837, we have this solid generated by rotating the region bounded by the function y equals x squared, which is this whole graph right there. And the point end line y equals 10, which is this horizontal line right there. And it's being rotated about the y-axis, which is why it's spinning horizontally. And we're just going to quickly, this is kind of a review problem to start us off with. So in question A, what type of slice is formed? It's a disc. You can see there's no holes in it, so you don't require the washer method here. It's just going to be, if you were to slice it horizontally, you're just going to get a circle, or a circle with a little tiny thickness, which we call a disc. The thickness of the slice is dx, or dy in this case, because we are slicing it horizontally, which means we're slicing a little bit tiny thickness of y with each slice of this thing. The radius of the typical slice for question B is where we have to do a little bit of math, because this is the function y equals x squared. But in order to think about what the y value is, or what this distance is there, along there, if you want to think about with a bracket, in order to do that, we're going to have to solve this for y. It's going to be true that x is going to be equal to, I guess, plus or minus the square root of y. Although we're probably only going to need the positive side of it, because we're only probably going to worry about this positive graph right there. So I'm going to go ahead and get rid of the plus and minus. I'm just going to write the square root of y. So that's what I think the thickness, or the radius of each circle is the square root of y. Right there. We have to kind of turn the function on its side a little bit. Question C, they're asking us to write and evaluate an integral to calculate the volume of the solid, which is relatively easy to do. We're going to go an integral from 0 to 10, because we're starting at 0 and moving our way up to 10. And for that, we're going to need to put a pi out in front, and the radius is the square root of y squared times dy, just like that. There's kind of a pi times radius squared pattern going on here. We're just adding up all of those circles, which is what the integral does. It adds up stuff over time. It adds up all those pi r squareds. You can imagine making this thing by stacking a bunch of pieces of paper that get progressively bigger as you go, and you have this kind of vase shape. That's exactly what we're thinking of here. Of course, if we're going to evaluate this, we don't need a calculator for this one. It's relatively simple to do. The square root of y squared is just y. So this works also. And to evaluate this, we are going to need to think about antiderivatives. So this would be equal to pi times the antiderivative of y, which is just y squared over 2. We have to evaluate that from 10 to 0, which is really simple because if you plug in 0, the whole thing just becomes 0. So this is pi times 10 squared over 2 minus 0 squared over 2. And 10 squared is 100. 100 divided by 2 is 50. So this is equal to 50 pi. So far we've looked at a really kind of a simple problem of how we would do this, just stacking up those circles right there. Question D is very similar. Now we have Xavier who's coming along, and he prefers to use functions in terms of x. So he's done a little bit of prep work. He used the inverse function. In other words, he took y equals x squared, and he did kind of what we wrote. He wrote it as x equals y squared, and then he switched the variables. Or sorry, x is the square root of y. And then he switched the variables. He said, okay, how about if I graph y equals the square root of x and just turn this entire problem on its side? So what you're seeing right here is the curve y equals the square root of x, which if you really think about it, if you look at these two pictures side by each, are they any different? I mean, one of them has the curve as the square root as x squared and is being spun horizontally. The other one has the curve as the square root of x, but it's being spun this way. Well, these should result in the same volume. And we're going to prove that right now, actually. Using Xavier's diagram, we're going to set up an integral and show that the method will give the same volume. If you follow the steps, if you look at what he's done here, you will get the exact same answer. Because it's the integral from 0 to 10, because this is 0, and now you got the vertical line, x equals 10, instead of the horizontal line, y equals 10. But it's still an integral from 0 to 10. And now it's pi times the square root of x squared dx. But this is the exact same integral. The only thing that's different is the name, x or y. It doesn't matter. All the math will shake out to be the same way. So this is pi times the integral from 0 to 10 of x dx, which we already know is 50 pi. We don't need to do it again. We already did this. So there's kind of a hidden lesson inside of this kind of warm-up, practice-y looking example, is that you can take any sort of 3D revolution problem like this, and you can use the inverse to flip it onto its side and get the same volume by spinning it vertically instead of spinning it horizontally. And so depending on how you want to think about that, it could be easier or more difficult to do that. I tend to go with Xavier. I like to think about things vertically, but it doesn't matter too much. We're going to look at a bunch of similar problems like this today. So let's look at 838. I don't know where I got 82 from. 838. So we got a range here, or a little area. It's the region bounded by y equals x squared and y equals 2x. 2x would be the straight line that's right there. And the x squared is the parabola that we're seeing right here. So we got kind of our boundaries. That's the line y equals 2x is the green line, and y equals x squared is the red line. And I believe the question in general, before we read the directions, I believe the thinking we're going to do on this problem is, would it matter if you took this region and spun it horizontally, or if you kept it right where it was and spun it vertically, would you get a different volume for the resulting solid? And unlike the last problem, we're not going to turn it on its side, or we're just going to keep it right where it is. Will the volume be the same if you spin it horizontally or spin it vertically? That's the question that we're going to ask or answer. So that's exactly what question A says. Imagine the different solids formed when the shaded region is rotated about the x-axis and about the y-axis. Will the volumes be equal? And if not, which do you predict will be greater and why? This is a good opportunity for you to make a prediction right now. If you're watching this video after the fact, or if you're right now in class, will they be the same or different? And if different, which one will be bigger, the horizontal spinny one or the vertical spinny one? Now, I have not done this problem yet. I looked at it, thought about, can I do this one live? But I think the vertical one was bigger. I think so. That seems to be the vibe. Yeah, it seems that the vertical one will it'll just have more stuff moving around. So we'll see that. In question B, we're actually going to do the work here. For question B, we're going to look at, we're going to sketch the solid and show a typical slice if the axis of revolution is the x-axis. And we're going to do the same for the y-axis. And then for each diagram, label the dimensions of a typical slice, set up and evaluate the integral. So let's do x-axis first. I'm going to need a lot of space for this problem, so this is for part B. And so we're going to do just a quick sketch of this. The point of intersection is the point 2, 4, which I think is important for drawing the diagram. That is the point 2, 4. So we have got the line y equals 2x happening right there. And we've got the parabola, which looks something like that. And we're going to be rotating this thing around the x-axis. So I like to start drawing the most extreme circle this way. You can see that it's going to have this kind of a outer edge like that. The inner edge will be the curve. I need to get a new pen because this one's too wobbly. Look kind of like that. It's tough to visualize this one because it's very tall and very skinny. But what we're going to do is we're going to think about the typical slice, which if you were to slice this thing with a kind of a vertical plane like that, you would get a washer in here. And that washer would have an inside circle also. And it's getting a little busy in this diagram, but I want to draw this washer off to the side in kind of a two-dimensional flat view of it like this. I'm getting a phone call. Who's calling me right now? Stuart Paul? Who are you? Screen? Doesn't matter. Now, a really, really good tool for these kind of problems is thinking about the outer radius and then the inner radius of each one of these circles. Because if you slice it, you're going to get a washer. The outer radius, what we usually call capital R in this problem, that's going to be determined by the straight line, the 2x. That's right there. And since we are doing this vertically, we can just use the original function. So the outer radius is going to be 2x. And the inner radius of the ring is going to be determined by the x squared. Right there. Since it appears that the 2x function is always above the x squared function, at least on this small range from 0 to 2. Like that. So if we're going to talk about the area of that general slice right there, it would be pi times 2x squared minus pi times x squared, like that. In other words, you take the area of the big circle and subtract the small circle. Both circles have an area of just pi times radius squared. If you want to turn this into a volume, which we kind of do, because these actually are three-dimensional, these washers. They have a tiny little thickness to them. So if we wanted to turn this into a volume, first of all, I'd factor the pi out. And you could, I suppose, if you wanted to, you could expand those into 4x squared minus x to the 4th. But then we need to multiply the whole thing by dx, which is the thickness of this slice. Because we are actually thinking about this as a little tiny bit of stuff right there, dx, like that. So when it comes to setting up an integral, we're just going to kind of put an integral in front of this thing right there. We just need to run it with the proper bounds. So our total volume here of this three-dimensional solid is going to be pi times the integral from 0 to 2 of our little function there, 4x squared minus x to the 4th dx. You know, typically when I'm teaching this, I don't encourage people to do x squared squared and make it x to the 4th. I like to keep it as like 2x squared or x squared squared because it helps to see the bones of the problem. But this is not too much of a jump there. Because we are going to compare the actual answer here, we should actually go on a calculator and tell what this answer is. So here's where I'm going to scroll over here. I'm going to pop up and put, you guys can't see I'm recording this right now, but let me move it over here. You can see the recording. That's great. I'll bring calculator cam up to the front there. And we're going to carefully plug this into our calculator. We're going to go to alpha F2 and pick out our fn_int tool. We're going to go from 0 to 2. Oh, we're going to put a pi in front of this thing too. And we're going to carefully type in parentheses 4x squared minus x to the 4th dx. Just like that. And this should give us something we can work with, 13.404 or something. Usually if you divide the pi out and ignore it, it's usually a pretty decent fraction. Looks like it's 64 pi over 15. These are good examples of integrals that are reasonable for you to do on the AP test with no calculator. It's not terrible. You could do it, but they typically won't ask you to do that because they're trying to test you on your calculus knowledge, not on your algebra or computational knowledge. So they try to shy away from questions that take a ton of time for the actual computation. So, and we're going to do the same thing here. We'll focus on how to use the calculator to answer that question. So this is the one that I think is going to be bigger, or they might be the same. Who knows? For the second part of this problem, we're going to do that exact same thing again, only this time we're going to rotate it horizontally around the y-axis. So let's set it up. This is for part 2. This is the y-axis version. Again, we're going to kind of set up our picture here. Oh, I should give it a little more room horizontally to draw. Again, we're going to remember that the point 2, 4 is kind of the key point here because that's where those two graphs meet. You get your diagonal line right there, and you get your parabola. I try to remember that the parabola has to go through the point 1, 1, so that's kind of the target that I'm trying to hit when I draw that. And then this time we're going to spin the graph horizontally. We're going to spin it around the y-axis, and so our graph will look something like this with a little, kind of like that. And over here at -2, 4 is where it's going to hit. So there is the diagonal line, and now there is the, oh, I want to do that in red. Like that. Kind of cool. We're going to spin that. Now, we want to, in order to think about this washer, we really want to think about it as a horizontal slice. So if you could slice this thing with a horizontal plane, you would, again, you'd see a ring. You'd see a washer develop. It'd be a circle, then another circle inside of that. Like that. And so again, to really wrap our head around what's happening here, it's a good idea to think about that ring on a two-dimensional, like head-on surface like that. Again, the question is, what is the outer radius and what is the inner radius? How can we express those two things? The first challenge here is that we're connecting everything back to the y-axis. And when we do that, we want our graph to be in terms of y and not in terms of x. So we got to take kind of our two functions. We have y equals x squared, and we have y equals 2x. We kind of want to solve these for x. We want to find the inverse version of those. So for y equals x squared, we've done this one already today. X is the square root of y. And for the other one, x is equal to y over 2. So we're going to be using these two equations inside of our parabola because we are, again, we're trying to measure, I say parabola, inside of our graph because we're trying to measure these distances. What's the distance from any point on the y-axis out that way? And what's the distance between any point on the y-axis towards that line right there? Turns out you can get those by using the inverse versions of these formulas like there. So I suppose the outer radius of any one of those rings is the square root of y, and the inner radius would be y over 2. So already some things are different about our calculation this time. And again, we have to remember there's actually a bit of thickness on this, which we're going to call dy this time, because that's terrible. Let me try that again. Oh no. Shoot. I want to do a better job. There we go. Perfect. So if we think about the area of that circle, it's going to be pi times the square root of y squared minus pi times y over 2 squared. Like that. The area of the outside circle minus the area of the inside circle. Just that this time we had to do a little bit of thinking to get it to be in terms of y instead of terms of x, because we're talking about the distance from the y-axis, not the distance from the x-axis. If we want, again, just like last time, if we want to change this into a volume, which we do, let's go ahead and factor those pi's out. And we can do a little bit of crunching here. Square root of y squared is just y. And then y over 2 squared, we can call it y squared over 4. And we have to multiply this times dy, which is the little tiny thickness this time, because, again, we're slicing it horizontally. So remember, dy means a little tiny bit of y. So that's what that thickness is. And then to evaluate this, we're just going to set up the integral. And this time we have to remember that we're going horizontally. So we're going to go from 0 to 4 with this integral instead of 0 to 2 like we did when we were vertical. So things are a little different this time. And the question is this going to be the same volume, or will it be something different? This is the integral from 0 to 4. I'm going to put pi in front because it factors out. And we have y minus y squared over 4 times dy. That's going to be the total volume of our three-dimensional revolution. And again, this is not terrible to do by hand. It would just be an antiderivative that we would plug in 4 to. You know, it's easy enough to do by hand. Let me try it. Let's just give this one a shot. We'd have pi out in front. The antiderivative would be y squared over 2. The antiderivative of y squared over 4 would be, well, it's y squared over, or y to the third, rather, whoops, over 3 times 4, which is 12. That's probably the biggest jump here. If you're going to try to do this without a calculator, is that if you're doing the antiderivative, you got to go to y to the third power over 3, and 3 times 4 is that 12 there. If you take the derivative, the 3 will come down and make 1/4 with 3/12 there. And then this is evaluated from 4 to 0, which is nice because if you plug in 0, it's 0. So you really just got to plug in 4. And again, I'm just trying to do this one without a calculator just for fun. You could easily put it in a calculator. Plugging in 4 would give you 16 over 2, which is 8. And plugging in 4 there would give you 64 over 12. And if we think about that, let's see. 8 is going to be, if I multiply those both by 6, 19 times 6, this is 96 twelfths minus 64 twelfths. And 96, I'm cracking, I'm going to use a calculator. 96 minus 64 is 32. So this is, oh, there's a pi there too. So this is 32 pi over 12, which will reduce down because 32 divides by 4, and so does 12. So 32 divided by 4. Man, I'm no better at this than I was when I was in school. It's going to be 8 pi over 3. Is that what you got? Yes. Nice. Which is approximately, hang on, 8 pi over 3 is approximately 8.375. Hey, I was right. So not only are these answers different, but the vertical one is bigger. You can kind of see them side by each right now. This is a good time. If you're watching this video after the fact, now's a good time to pause because all the notes are there. They're a little small, but you can see both of them. They do kind of give you a couple of different answers there. The vertical one ends up being bigger, I suspect, because there's just more motion. You have to move more stuff further, which is why it creates more volume. The horizontal one all seems pretty clustered close to the y-axis. Like that. Pretty cool. Question C, that's kind of the answer to question C. What accounts for this difference in volume? I think it's the height, that you're further away from the y-axis or the x-axis, depending on that. So let's look at the next question, 839. Take a look at one more example before we add one more last thing onto this that we have to add on. So this time we're sketching the region bounded by x minus 2 and x squared minus 4. And we are asked to calculate the volume of the solids created when the region is revolved around the x-axis. Be prepared to explain and justify your method to the class. Also be sure to introduce key features. So let's just go for it. We have x minus 2. Let's try to sketch this picture really quick. Thinking ahead about these functions there, x minus 2 has a y-intercept at negative 2 and has a slope of 1. So it's going to be kind of a straight line. I'm going to use a ruler just to get a good picture of it here. It's going to look pretty much like that, x minus 2. And then x squared minus 4 is a parabola that has a vertex down here at negative 4, and then it has a basic parabolic motion from there. So I believe the first intersection point is right here at negative 1, negative 1, negative 3, and then comes down like this, and then it makes a parabola, 1 over 1 up 1, and then back up here is the next intersection point. So it looks something like this. And that is the point 2, 0. Those are the two intersection points. So our challenge here is to revolve this around the x-axis. So when we do that, we're going to kind of a weird-looking shape. We'll have kind of like a bowl. You'll have the same kind of like shape mirrored up there, and then you'll have just kind of this rounded edge to it. Which you can put a little ring on there if you want to. Something like that. So we got to think about this the same way we think about all these problems. We're going to start by giving it kind of a vertical slice and thinking about the washer that will develop from this problem. Again, if we pull that washer off to the side and really think about it in terms of what the inner and outer radius will be, it looks like the outer radius is always going to be the parabola function, and the inner radius is always going to be given by the, that's interesting. Oh yeah, no, it's correct. The inner radius will always be given by the straight line function, just like that. It is kind of interesting because we have this, all this stuff is down below, but it doesn't really matter. It's all going to be positive anyway. What I suspect might happen when we run this calculation is we might get a negative answer from our calculator, and we'll just ignore that because volume would never be negative. It's just representing the fact that all of the area is below the x-axis right now, but the problem is still going to be done the same way. In fact, we can pretty much run through it right now. The outer radius is going to be given by the x squared minus 4 function, and the inner radius is going to be given by x minus 2. So this problem is going to shake out pretty similar to the last few. The area of any given washer is going to be pi times x squared minus 4 squared minus pi times x minus 2 squared. I'm just showing all of the work here. At this point, you're probably familiar with jumping ahead a few steps because it's the same stuff every time. But I am just showing you everything going on there. It's the area of the big circle minus the area of the small circle. And then for the volume of each one of those, you factor the pi out. And this is a good case for not expanding everything out because it's not going to be cool. I'm going to use a square bracket for the big one. I mean, you can expand x squared minus 4 if you wanted to out. I'm sure some stuff can't combines, but not worth it, in my opinion. And then, of course, we got to put a thickness on there if we want it to be a volume instead of an area. And so our integral that we're going to set up is going to be the integral from -1 to 2, because that seems to be kind of the left bound and the right bound of our problem, -1 and 2. Right there. And we will go from, we're just going to run this calculation on our calculator. It's going to be x squared minus 4 squared minus x minus 2 squared. And I'm sure, I mean, it's probably going to be something pretty reasonable because that integral will probably be something. If we're to work it out by hand, it'll be something like a nice fraction. But we're just going to use the calculator to muscle through it because it's going to be much easier for us if we do that. So I'm just going to bring the calculator up and we're just going to really carefully program this in. I'll start by typing the pi. Alpha f2 gives us the integral. This is from -1 to 2. And carefully in the first parentheses, I'm going to do x squared minus 4 close parentheses squared minus in parentheses x minus 2 close parentheses squared dx. I think, whoops, dx. I think that will do. I'm just going to give it a quick look to make sure it looks correct. And then I'm going to push enter on it. And I suspect, oh, it does take care of the positives for us, which makes sense. It's going to square it. So, yeah. If we divide the pi out, I wonder if it's anything nice. Oh, it is. 108 pi over 5. Not too bad. Which is 67.858. Units cubed, I suppose. These are volumes after all, so. Go ahead and put that on there. Not so bad. This is a pretty straightforward process, and I hope after seeing, whether you're watching this after the fact or whether you're with us, I hope you guys are feeling like it's kind of like, oh, it's the same thing every time, which it kind of is. There's only one last thing that we can throw at you, and it would be this last question that we're going to look at together right now, which is this problem right here, 840. We have the region bounded by x cubed plus 1, which is this function right up on top there. And we have the line x equals 1, which we see, the vertical line right there. And then the x-axis itself. We're going to set up and evaluate the integral that will calculate the volume of a solid created when the region is rotated. We're not going to evaluate it. We're just going to set it up. For the interest of time and repeating the same thing over and over again, we're just going to set it up. So for question A, we're going to skip all those other steps and we're just going to go for it. I think it's pretty clear from this that if we're going to rotate around the x-axis, we're looking at pi times an integral from -1 to 1. Since we're rotating from -1 to 1. And this is just going to be disks. There will be no washers because there will be no hole in the middle. The function on top, in the bottom edge, is the axis of rotation, so there's no hole. So all we got to do is put that function in there. It's x to the third power plus 1. So x to the third power plus 1 squared dx. That's it. And there's not really much more to say about this problem than that right there. It's just what it's going to be. You could, at this point, plug in the calculator if you want to, but that's okay. That's kind of the first part of this is set up that this is an easy problem. But question B is going to throw a bit of a curveball at us. What if the region was instead rotated around the line y equals -1? So in other words, what if the axis of rotation was not the x or the y-axis? What if it was some other line, which would be y equals -1? We have a kind of a picture sketched, set up all ready for us to think about that here. So this is the new axis of rotation. So what that's going to do for us is it's going to kind of put a hole in the middle of our three-dimensional revolution. Instead of it being a solid mass, now it's going to be kind of like a, I don't know, like a little tabletop paperweight with a hole in the middle of it. If we start thinking about this revolution now, like this, now we're suddenly going to have washers instead of discs. So we have a little bit of a gap in there. And so we have to think about what the resulting, it would be kind of like this, what the resulting solid would look like, but then also, how are we going to think about the volume of this? Again, if we come through and slice it vertically, every cross-section is going to be a washer. The nice thing is that the washer is going to be pretty straightforward to deal with because the outer radius is still going to be the function, the same function it was in the previous problem. The inner radius, though, is going to be a very consistent 1 because now the inner radius is 1 away from where we used to have the axis of rotation. So if we think about, for part B, we think about any one of those washers for a minute. And we really think about outer radius versus inner radius. The outer radius is still the function. It's the same thing. Well, it's a little different, though. It's not quite the original function. It's still x to the third plus 1. But the challenge, if I get rid of all this other stuff in the picture, the challenge is to express this distance right here. Which is pretty easy to do if you think about it, because this part of it is just x to the third plus 1. And this part of it is just 1. So the outer radius is just going to be the wavy function x to the third plus 1 more to get to the inside of that revolution. So our new outer radius is actually x to the third plus 1. And I know 1 plus 1 is 2. And I know you can combine those like terms, and I certainly am going to, but I really want you to see that the plus 1 in this problem came from the fact that we added a little bit of space now between where the function is and the axis of revolution. The inner radius is a very consistent and very boring 1 because that's what it is. It's never going to be anything different than that. In fact, we're now talking about the distance between the axis of rotation and 0. With this information in tow, this problem becomes the same as every other problem. Nothing really is new about it. This is still going to be, the total volume is still going to be pi times the integral from -1 to 1. Only this time you really got to think about your different radii here. The outer radius is x to the third plus 2 squared minus 1 squared dx. So it's not super different. It just requires a little more thinking here and here. How do you express the outer and inner radius if suddenly you have to do a little bit of subtraction or addition? It depends where it is and where you're doing that, if you're going to do subtraction or addition. That's it. Let's take a look at a couple more examples. I think they've given us a couple other ones to think about. Oh, we already answered question C. We did it along the way. We answered question B and question C. Question C asks for the typical slice from part B. What's the radius of the inner circle and the outer circle and how it's related to the graph. And we also calculated the volume. So question E says Tran is an ace at shifting graphs and has shifted the shaded region from part B up 1 unit and then rotated this new region about the x-axis. Should Tran get the same volume as in part D and set up and evaluate an integral to verify the prediction? So we're going to do one more of these. This time, looks like we're going to keep the axis of rotation as y equals -1. But this time we're going to take this entire area here and we're going to shift it up one space. So now it's going to look something like this. And we're going to rotate that around the line y equals -1. Well, if we learned any lessons from the problem where we rotated horizontally or rotated vertically, we kind of know the answer to the question is going to be no. It's going to be way different. It's probably going to be way bigger. And we'll run the calculations at the end to confirm that. But this problem is very much the same as the problem before it. All we got to do is think about what is the new inner radius and what is the new outer radius of this shape we've created. And I'm putting them kind of on the end, but you don't have to. It's just the same basic shape, just the hole is bigger now. So we still need to think about the inner radius and the outer radius. And I'm going to do this over here as part D. Let's go ahead and draw another kind of generic washer and think about what these new radii are. So the outer radius this time, you still have the function x to the third plus 1. But the difference now is, okay, what's this distance from any point on that function down all the way down there? What's that distance there? And it turns out it's kind of the exact same idea. It's just going to be x to the third plus 1 plus 2, because now we've got a space of 2. We moved the function up one space. We left the axis of rotation one space away. So now we got to add 2 on there. So over here, our outer radius is now x to the third plus 1 plus 2. And again, I know 1 plus 2 is 3, but that's not the point. It's to see that we actually moved it up one space and moved the axis one space away. So we're adding a little bit of space to that outer radius. The inner radius is just going to be the same kind of thing as last time. It's just 2. Very boring. Very consistent all the way throughout the rotation. And so the integral ends up being kind of the same thing. It's pi out in front, -1 to 1, big square bracket. This time the outer radius is x to the third plus 3 squared minus 2 squared. Which I guess you could put 4 in there, but who cares? dx. Again, it's really important in these kind of problems to see the bones in the structure, so that's why I'm not doing a ton of simplifying along the way. So the only last thing we should do before we close this and give you guys some time to work on whatever you got to work on, we should run these 2 calculations right now. I'm going to move this all the way up there, and we'll see how they compare. I'm guessing right now that this one will be bigger on the right side because we're adding more vertical space to the rotation, which will probably make it a little more hefty when it comes to that. So let's go ahead and run those calculations here right now. The first one is going to be pi times the integral from -1 to 1 of, in parentheses, x to the third power plus 2, close parentheses squared. Oops. Minus 1 squared. I'm only typing that 1 squared there because what I'm going to do for the next calculation, I'm just going to copy this and change one of the numbers. So the first one there is 19.747. Which I'm adding to the notes underneath this. And if I divide by pi, it's going to be, oh, that's not fun. Oh, look at that, 44 pi over 7. That's fine. For the next calculation, I'm going to use the old calculator trick of arrowing up to my past thing and pushing enter so I can edit it. Because the other calculation is basically the same. We just changed the 2 right there to a 3, and we changed this 1 to a 2. Basically added 1 space to our revolution. And yeah, it's a little bigger. It's 32.314. And if I divide out the pi, maybe it's something nice. Oh, it's 72 sevenths. There we go. Not too bad. Makes me wonder if there's some sort of connection between 72 sevenths and 44 sevenths. Like 72 divided by 44. No, I was thinking maybe there'd be some sort of interesting relationship to these numbers that we added 1 space of revolution to, but oh well. That's it. These problems, if you're at the end of the video or whatever, you're live with me, this whole section comes down to map out your washer, figure out what your radii are, and then set up the integral. But give some thought to what those radii are. And sometimes they go horizontal, sometimes they go vertical. Sometimes the axis is something else. I'm just going to have a circuit training for tomorrow, which has a bunch of practice problems on this, and then I'm not going to give a quiz over this because it's not worth the time. And Thursday and Friday we'll look at some free response questions and some scoring guides and give you guys an idea of what you're up against when you go in on Monday. So that is the plan. This is the last homework section that I'm assigning from this textbook for the year, which is fun. I have recorded 41, 42, and 43, and we're not doing 44. We're not doing 45. And I recorded 46 also, but I still have to record 47 and 48. And then that's it. Yay! I'm gonna stop this video. I'm gonna upload it to YouTube.